Salutations, and welcome to Space Time Continues. My name is Mary Louise Davey, and let's get started. Okay, we're going to go to space. We're going to watch the SpaceX launch that just recently was the cargo load going up to the ISS. And then I'm going to watch the rocket stage coming down before I start into our stories for this episode. Now, as of today, the cargo load to the ISS had a reboot. It was heading there, but it wasn't quite aligned properly. And so according to the way it is set up, it is supposed to do this. It is going to go back and redo another alignment. So, nonetheless, this has been a very successful launch. So, the ISS will get its cargo. I think they're talking tomorrow now. And in the meantime, let's view a really great launch.
5, 4, 3, 2, 1, ignition and liftoff of the Falcon 9 to the space station on the first commercial launch from Kennedy Space Center's historic Pad 39A.
So that was really cool, right? I mean, who doesn't love a good launch? But the really cool part was the rocket stage coming right back to Earth. It just looked like it was almost in reverse. Just took the film and reversed it. It was beautiful. And it leads me to my topic today, space debris. Well, Elon Musk and SpaceX are doing tons to take care of the future of space debris. However, we still got all this space debris that we've managed to collect over the years. 500,000, million, depends on who you ask as to how much space debris there is. Back in 2010, I used to do a presentation that part of it was on space debris. And back then it was 500,000 pieces. Now today when I checked, some said 500,000 pieces, some said 1 million pieces. There's 10,000 to 20,000 rocket stages up there, large debris. So it really varies on whether you're measuring the ones that are the size of a screw or the ones that are the size of a full satellite or a CubeSat. But nonetheless, space debris is a real problem. And it's going to, at some point, if not immediately, interfere with somebody taking off. They'll be heading up through the atmosphere, and then bam, space junk will run into them. So we have to take care of this problem. And speaking of which, Japan, on the recent, and by the way, kudos to them because they have now joined the US, Russia, and the ESA in delivering goods to the ISS. And they were testing a space debris mitigation system on their way back to Earth. But unfortunately, that didn't quite work out. It never sent out. It was supposed to send out a tether out about 700 meters, which is 2,300 feet. But it never deployed. And the engineers were given a week, and they had a week to play with to get it to do that, but it didn't. So then it completed the rest of its mission, because the mission from the ISS, it was going to be filled with junk that it would destroy as it went down and burned up in the atmosphere. So that part was extremely successful. It's just the test didn't quite work out. And it makes it a little more difficult for the engineers to figure out the problem for next time, because it might have been really simple as I don't know, it just didn't deploy, could be anything. The device itself could certainly have been workable. And when is Japan going to try it again? They'll probably check it out the next time they're doing something like going up to the ISS again with cargo. Regardless, it'll work out. And this year also, the UK is going to be testing its mitigation system. And in 2023, the ESA. There's also some really good news last week or the week before. DARPA and MDA, that's McDonald Deatweiler and Associates of Canada, are striking a deal and working on something. Now, you may remember the MDA from years ago, about 2013, where actually roll back to a little before that. We were testing up on the ISS a faux satellite that we would place up on the ISS. So we'd place a faux satellite, and then Dexter, that's the space arm, the Canadian space arm, was going over and pretending to refuel it. And this was in hopes of refueling satellites that are all out there, that once they run out of fuel, they're just done. So we spend millions and millions and millions of dollars getting a satellite ready, then millions of dollars getting it up into orbit, and then when it runs out of fuel, oh well. Well, this was hopefully to figure out how we can get past this, how we could go back, send something out there to refuel the items. And this way they don't become space junk. They remain an active satellite. I mean, think of it. It's like buying a brand new car, Maserati, say, and you fill it up with gas, and this is wonderful, and you're out cruising, and maybe you went to Big Sur, maybe, who knows where you went. But you're enjoying it, it's great, it runs out of gas, and you just park it on the side of the road and walk off because, well, it's out of fuel, so oh well. That's what it was coming down to, and that's why DARPA and MDA are teaming up to run through with this same thing that they already did testing of the idea, concept testing, up on the ISS of the faux satellite. And they found out it was possible to fuel. Older satellites have a harder way of getting into the fuel. They're not meant to be refueled. So they wanted to make sure that they could do this. So that was done way back in 2013. Way back in 2013. So now DARPA and MDA team up today to actually come out with something to take care of this systemic problem. Okay, so let's discuss what other possibilities are there. Well, when it comes to space junk, there's Impulse. Now, Impulse is a methodology that works off of taking future satellites and future rocket stages and changing the way they're made. This uses an A-B braking system that would drop them out of orbit, decay, and then burn up. Or an A-B parachuting system that would save an expensive satellite from burning up and let it come down gently, down through the orbit. So the giant laser, that's a cool one. Okay, so you shoot up, you wing it, and it decays the orbit and it brings it on down, and voila, no more space junk. Or they were thinking of a laser-based ISS system. A laser on the ISS that could shoot off at various space junk or satellites that are circling that are dead and bring them down, decay their orbit. But there were problems with that because of A, that weaponry in space that people don't seem to like too much, and B, what if the country controlling the laser suddenly starts shooting another country's good satellites down? Well, I think this could be overcome if they just had it on the ISS and had whatever countries are present had to be present during the firing of the laser. So it wouldn't be just the US or Russia, but it might be China or JAXA or Canada. All the countries are present at the time of the firing of the laser to bring down the space debris. So I think it could be worked out, and it's a good idea that will probably result in a lot of junk being mitigated. So why not give it a shot? Give it a shot. That's good. There are other ideas. There are ideas such as, then there's the self-destructing satellite, and this is kind of cool. It's Swiss's Space One, or Clean Space One. is what it's called. And it's very similar to Miss Pac-Man. So it goes up and it gobbles. Now, this is actually being made for one satellite, just one. So it's a CubeSat. It's not even a humongous satellite. It's a little satellite. So they must really want that back. But regardless, it goes up, swallows it, and then both of them go down, and both of them are destroyed. So you spend all this money on this one satellite to go get this other satellite to then both of them go down and die. So the Swiss must think it's worthwhile. I'm not sure about the ROI on it, the return on investment, but they must think it's worthwhile. Another idea, which is rather interesting, is the wall of water. Now, this is done using decommissioned missiles. So you send it up, and it drops its payload. Now, its payload is water, so that's not too expensive, right? So you use decommissioned missiles. That was a money savings, and you're using water. Now, you're dropping it through the system. So now you've got a wall of water. So now any satellites coming along or space debris, boom, run into the water, it slows them down, decays their orbit, and they go down. Minor problem. You've got this wall of water that really can't tell the difference between good or bad satellite, space junk, rocket stages, what have you. It won't know if something's a good communication satellite or something that it's supposed to be getting rid of. And so no matter what goes through that, it's going to decay and fall from space, fall from orbit. And we have the tungsten microdust. Now, that works very much like the wall of water, except for it's tungsten microdust, which, the water is really cheap. Why should we try that? Now, tungsten microdust, so you know what it is, it comes from meteorites, or it comes from about 5%, I think, of the Earth's crust. So there's that combination. It's also somewhat toxic. So I would think that would eliminate that as a possibility right off the bat. I don't know how much is going to come down when they put it up there. I don't know if a lot of it or just a little bit, or there's a slight chance of it coming all the way down to where we are. But I think any risk is too much if there are other ways that do the exact same thing. And wall of water does the exact same thing. It takes anything that goes through its path. So we're good with that. Now, next is the electromagnetic debris eliminator, EDI. And EDI has electrocharged magnetic nets. It's a long strip, and it's filled with net managers. And when a net is unfolded, it's about the size of a house. And it's the same thing as everything, just pulls it and goes on down. It also takes its energy from the sun and also from the Earth's electromagnetic field. So nice and cheap energy, keep on going, pulling that junk down. Now, the next we have a short film about DARPA's Phoenix program. Let me give it over to DARPA. Now that's pretty cool because it's logical. Because as I told you before, you know, the expense attached to it and just walk away because it has no fuel. And DARPA has the idea of, well, no, we can actually use those parts. So I like that a lot. Sticky Boom is another one of the space debris concepts. And it's a robotic arm named Sticky Boom. And, you know, it goes out, it's got this sticky boom, and it sticks to anything. It doesn't matter the size, doesn't matter the shape, doesn't matter the material it's made with. It will grab it and then bring it on down. And then there's the Space Debris Eliminator System. That's by Raytheon Technologies and funded by NASA. And that fires targeted puffs of air. It's a targeted puff of air, and then any space debris goes through that and it decays it because it slows it down, messes with its travel. Now, this may be good or it may not. I'm not sure, because the wall of water takes anything in its path, and obviously it's a wall. The targeted puff, how big is this puff? Is it small enough that it will only take, well, we monitor satellites. So, okay, we're monitoring and now we got a good satellite coming and do the puff quick because there's a bad satellite behind it. Or is it the kind of thing where you send a puff and oops, it's a little big, it's kind of going to get that good satellite too, in which case, obviously, I'm going to have to say pass. So, Europa, one of my favorite topics actually. Very cool planet, icy planet, one of the icy moons of Jupiter. One of the icy moons that has liquid oceans, which we know is water. How do we know that? Very easy, actually. Okay, here's Jupiter, and Europa's got an elliptical orbit. So when it's over by Jupiter, it's nice and round. Now the gravity on Jupiter is extremely strong. So now the gravitational pull as it goes out stretches it a bit. So the ice cracks, we get fissures along the top. And then as it comes back, then boom, goes back to a sphere. So stretch, sphere, stretch, sphere, slams together, a geyser is pushed out, water goes out into space, and looking through a telescope and using a spectrograph, we now know that's hydrogen and oxygen and hey, that's water. So now we know there are liquid water oceans on Europa, but it's beneath all this ice, and besides being beneath the ice, there's this minor problem of lethal radiation. So if we were to send a human to Europa, it would be a major problem at the moment until NASA's working on ways to mediate radiation. But right now, it still poses a problem. And so there's a flyby of Europa planned. But more than that, because NASA had thought, well, we're going to do a flyby, and they planned it okay, and they went to Congress and said, hey, this is what we have planned, and Congress mandated. That means they made it a law that NASA had to send a lander onto Europa. So now NASA's going to go by, and instead of doing just a flyby, actually 24 flybys, there's a lander that's going to drop down off of it. Now it's going to use the same methodology as was used by Curiosity. Remember that? Really awesome. It was where it held up and it kind of let it down that way. Well, that's how it's going. So it'll drop off the lander. The lander will be active for a while, and for I think 20-something days. It'll be active, it'll take samples, different levels of ice, although it can't possibly go through all the layers of ice because ice there is 9 to 11 feet thick, so there's a lot of it. But anyway, and get all these samples and everything and send information back up through the orbiter and back to Earth. And this way, we don't do a flyby where it takes so many years to get there and then do the flybys and send that information back and then think, okay, we got to put together a lander. Now send a lander, and that takes umpteen years. In this way, we find out a whole bunch of stuff on our initial trip to the planet. So we'll get all that. They really suspect that there's a lot of life on Europa. They suspect that in these oceans, because when you go down the bottom, there's like heating vents. So these heating vents in this warmed area, and it's got liquid water, might be life. Now the ice, most items that have hydrogen or something in them, work against radiation. So it stops the radiation from going beneath the ice. So theoretically, we could have a floating city underneath the ice. But I wouldn't recommend it. I would think that it would, during that time where it goes wide and comes back, goes like this, might send a geyser up and let some radiation in and, whoops, oh well. I think down under the sea, next to one of the heating vents, it'd be perfect. And that's probably where all the life would be anyway. So we'd have a wonderful view as if we were in our own aquarium. So we shall see. Now there's one thing I wanted to mention coming up in a couple weeks. The Lunar and Planetary Society is having the LPSC at Woodland, Texas, all about Europa. So glad to see other people think Europa is a number one. Now, think about Nancy Sinatra. What would you think that would have to do with space? Nothing, actually, but these boots were made for walking does, because MIT just started these boots. They have these boots ready for NASA, and they're really awesome because back when the Apollo went to the moon, it kind of clumsy, would fall, and on the moon that's not such a problem. And they weren't clumsy like the people were really clumsy. It was clumsy like these suits were so big and awkward and you can't really tell if you hit something, so you might trip over it. So NASA was thinking about what needed to be done. MIT was thinking about what needed to be done. MIT has worked it out. MIT has, here's the boot. In the boot, in front of the big toe, is a big vibrator. And a vibrator that, as you're approaching, say here you're approaching something that is solid. As you're approaching it, it starts vibrating, and it vibrates harder and harder as you get closer to it, like more seriously in warning. Now, in addition to doing that, it has a visual cue. A circle that's orange that becomes opaque when, well, you're there now. So think about this. If you fall on the moon, granted, it's more like the regolith, the lunar dust is a little softer than perhaps if you were on Mars. Also, the gravity's a little less on the moon than on Mars. So if you fall on Mars, which is a rocky planet, it could be a little more consequential. So you really want to make sure that doesn't happen. And so this is what's going to be used. And they're £1 each. They're using a 3D printer to make the boots. So very good job. Excellent. Now, think about Venus. This is, well, our sister planet, much hotter than Mercury, much hotter than any, well, at least on the surface, hotter than any planet in the solar system. It's got all sorts of gases in its atmosphere. It's got a very dense atmosphere, and it's even got sulfuric acid in it. So, yeah, it's a problematic place. But NASA's going to want to send things, and you want to go down, you want to visit little parts that you can, but if it's got the atmosphere like that, what are you going to do? I mean, computer chips, things like that, they can't survive it. So, NASA's been working on it, and now they have, thanks to their GEER, and that's the Glenn Extreme Environments Rig, GEER, G-E-E-R, this allows them to test something as if it were on the planet. It mimics all the atmosphere, all the changes, whatever you need. It uses up to 7 or 8 gases, and you can also add water vapor if needed. Whatever you need to do, the temperature mimics the whole bit. Well, they've had this chip, this transistor actually, 24 transistors, actually survive it. See, previously we didn't have a chip that would last long enough, so anything that went there would, okay, and sending information, no. So, now we're good. We're good to go, right? We've got this? Well, no, not exactly, because this chip has 24 transistors, and that would have been excellent if we were in 1970, but we're not. We used about 24 transistors then. Now we use about 2,200. We have microchips, we have, all these sorts of things that the conductive material, all of it is, we use a lot more. But then we make a lot smaller, but nonetheless. So, The problem is making 24 now 2200. Well, that's much easier than making 0 into 24. So we're in good shape there. Now, the available gases on Venus, just to show you how difficult this was though, CO2, N2, H2S, sulfuric acid, HF, hydrochloric acid, nitrous oxide, and CO, carbon oxide. So these are things they have to contend with. There are a lot of different things that we have to put up with, gases, etc., on other planets. They're not all like Earth. Earth is an anomaly. Earth is 1 out of 8 or 9, if theoretical planet 9 works out, planets. And it's the only one that is like Earth in this area. And you hear from Kepler that there's plenty of Earths being found, but in the percentages it is about 1 in 9, 1 in 10. So we got to figure out how to make everything we do possible, but in a much harsher environment. And the VAMP, have you heard of the VAMP? The VAMP that flies around on Venus, it's sort of like a glider. And it just glides around. It's, I won't say plastic because that would probably get eaten up by its atmosphere. But Northrop Grumman made the VAMP, which is the Venus Atmospheric Maneuverability Platform. And it's self-inflated, and it can stay aloft for quite some time. It doesn't have to have a motor keeping it up there. It's a glider, and it can just glide around forever. And probably with the dense environment would make it easy, actually, to stay up. But put that, get the chip worked out, put them together, and then we'll know all the details about Venus. Perfect. So then we have the twin study. NASA Twin Study, and I'm sure you've heard of this. With Scott and Mark Kelly, Scott went up to the ISS. He was the astronaut. Mark was an astronaut. He's no longer an astronaut. He's a retired astronaut, and he stayed on Earth. I imagine they had medical reviews prior to having gone up, to Scott's having gone up, but he went up to the ISS, 340 days, longest time. I think it lasted for a couple weeks because I think someone else was heading to longest time. But nonetheless, longest time up there. And they were worried about the health in traveling through space, or they just wanted to visit that because there's a long travel time to Mars before you end up on Mars, and then you want to stay on Mars for a while. So you're going to be gone a year and a half, 3 years. Depends how long they plan this to stay on Mars. But anyway, they're doing us. Now, they found exactly what they expected. I mean, muscles wasting away when you are up in space. On Earth, he got exactly as much older as the days that had passed. Increased pressure in the skull leads to possible eye problems. The heart gets smaller because it's easier to pump your blood with no gravity. As a matter of fact, they exercise in space about 2 hours a day. So if you were worried about your exercise program, think about that one. But there also is this thing called telomeres, and they're at the end of your chromosomes. So you got chromosomes and you got telomeres. Telomeres get shorter as you get older. Well, Scott's up at the ISS got longer. So theoretically, Scott was younger when he came down than his twin brother here on Earth. And so they're checking into all these things. They're going to find all these things out, and slowly it'll come up over time as they, analyze all the material, and they'll be able to help people, the astronauts. But better than that, they'll be able to help Earth people who haven't left this planet. They'll be able to help you and me. So anybody who ever worries that, oh, NASA does all this and that, but it's a waste of money because we have stuff going on here. NASA has always, all along the way, a lot of medical devices have come via NASA. All these things come from NASA. Oh gosh, I can't think of the medical tests. All these tests, all these abilities that we have to find things, a lot of them are based off of originally a NASA invention for space. So They help us out in so many ways. It's time we sent them a thank you card. Now, I wanted to update you on Proxima b. And as you recall, I told you lots and lots about Alpha Centauri and breakthrough initiatives and Yuri Milner. And Proxima b is not Proxima b, big B, but Proxima little b. So it's Proxima b and then the planet that goes around it. Well, we had thought that that was in the habitable zone. It's not, I'm sad to say. Or so they believe now. I guess we won't actually know until Yuri Milner sends a CubeSat there. But nonetheless, the scientists are saying that it loses too much atmosphere and oxygen to support liquid water, hence life. Now, before I continue the other problems they suggest, I have a problem with what they're saying. It doesn't support liquid water, hence life. I'm not sure I agree with that. It doesn't support human life. However, I do not believe that just because there's not water, there's not life. I think life always finds a way. And I think that all life is not necessarily carbon-based. And I'm waiting for the thing that I can research that will prove my point, my belief. But in the meantime, we'll just have to wait for Yuri Milner to send someone. The scientists have traditionally determined habitable zones, basing it on the amount of heat and light. Does it get enough of this, enough of that? But there's new research that bases it more on like stellar eruptions and things like that, even if it has volcanic eruptions on the planet itself. All these things contributing to gases that would then allow the oxygen to either escape or get eaten up by the creation. It's ultraviolet emissions given off by red dwarfs change their standards. But it's interesting because if you think of the planet or 7 planets actually that they just discovered, and they were saying, wow, we discovered 7 Earth-like planets and 3 of them are habitable. Read on in that article and you'll find that it's around a red dwarf. And then wonder if they applied the same things that they applied to Proxima b, did they apply that to, I'm not sure what that's called, Testeres or something like that? Did they apply that to this new planet? Because, I don't know, you're talking about a whole bunch of planets and a whole bunch of Earths, but they're around at a red dwarf. I mean, same could apply. So, it's one more comment to make, and I'm going to leave you with this. This is why I believe also in life. It has a lot to do with the quantity. I said before, we are planet Earth. We are the only planet out of theoretically 9, possibly 10 if you want to count Pluto as a planet. So, okay. So our planet is 1/10 of the planets, and it's only one that's Earth-like. It's the only one that will support life as we know it. Well, there's 400 billion stars in the galaxy, approximately. I didn't count them all. And out of those 400 billion, about 40 billion of them are Earth-like. So basically 1/10. So you're saying that 9/10 of those planets, 9/10 of 400 billion, so say 360 billion planets, all have all these planets, at least one planet each, and no life. You can't have any life on any of those planets. I'm not so sure of that. So, food for thought. And I'll see you the next time on Space Time Continues.